All right, we have seen now that there is a relationship between the potential difference and the electric field given by this equation here. Delta V is always going to be expressed as V final minus V initial. As you go from some initial to some final position, a charge in an electric field, this is the relationship then between that potential difference and the electric field along some path. And it turned out that since this is a line integral, the path doesn't matter because we're dealing with conservative forces here. All right, if we'll talk a little bit more about this in just a minute, but if you were to take this relationship right here and solve it to go the other way around, then the electric field is going to be the derivative of V with respect to S. For vector S. That's a unit vector in the S direction. So this relationship here, and there's a negative sign, that would be there as well. These are partial derivative signs. If you've never seen those before, a partial derivative is the same as regular derivative, except there may be multiple variables in the equation. You treat all of the other variables besides the S variable as constants. So really you're taking the derivative with respect to S, where all of the other variables you treat as constants. That's all that is. Again, like I said, we'll talk more about this, so don't allow this to confuse you at this point if you haven't seen this before. But in a more general expression then, this can be written as minus del V. And if you've never seen the del function before, then we will talk about that as well. The del, or also called, probably more correctly called, the gradient function. All right. But the important thing here now is that this is the general expression right here for the relationship between the potential difference and the electric field. And we derived an equation then for equipotential surfaces inside a uniform electric field. And just very quickly to review, if we have an electric field pointing in that direction, and we take a charged particle at this point, and we move it on a path down to this point. So this is its initial position, this is its final position, and the distance between those two places there, those would represent two levels of equipotential surfaces, one at the initial equipotential surface and the final equipotential surface there. Then delta V is equal to minus E times D. And we derived that equation last time. So we have used this equation up here to find the relationship between potential difference and electric field for a uniform and constant electric field. This is that relationship there. We should be able to use this equation here to find the potential difference due to other sorts of charge configurations, not just uniform electric fields. And that's what we're going to spend some time doing here. For example, let's say that we have a point charge. Here's the point charge. We know that the electric fields radiate outward into space in all directions around the point charge. Okay, question might be, if we come out here some distance away to a point that is r distance away, then what is the potential at that point right there? Okay, well, we should be able to use our relationship, this, in order to find out how that works. Well, in order to do that, let's write down the equation here. In general, V final minus V initial is going to equal minus the integral going from some initial to some final position of a point charge E dot ds. Okay, so that's the general expression right there. Now, in our case here, we could choose the initial position to be a place where the potential is zero. But where would that be? The only place that would be is going to be way out at infinity. So way off stage right here, out at infinity, we could say the potential is zero at that point. So let's go ahead and do that, and that makes this initial boundary then infinity, like that. And this is a possible integration to do for this point charge here. Now when we do that, what we're going to discover is that this V final is actually the true potential. So we might as well just call that V for a point charge. But it is the potential relative to the place where the potential is 0, which is at infinity here. Okay, well, we're going out here position R. We have to start then at infinity and go to some final position. So let's say we're way out here somewhere and we take our positive point charge and we are moving in this direction from infinity. That represents ds, the ds vector. Okay, the electric field out here is pointing radially away, so the electric field way out here at where the charge is going to point in that direction. Okay, well, we start out at infinity and we're moving and we're going to end up right there. That's going to be our final position. But notice here, the position is measured relative to the point charge. So we're a distance r away from the point charge, but we're coming in from infinity. So the question is, what is this distance from here out to here? We need to realize that we have a dr vector that points in this direction. It's because we're measuring our distance from this point charge. Any sort of vector that we talk about that's related to distance away is going to point in that direction. Okay, so this is necessary in order for us to be able to work this problem. See, we have a ds here, but our E equation for a point charge is going to be measured relative to r. So if we were to take this right here, the integral from infinity to r, and those are both distances measured from the point charge, is equal to E. Well, E is 1 over 4 pi epsilon naught Q, and we're assuming that our charge here is just Q, over the distance it is away, R. In fact, we can use the variable here, little variable R, because when we plug in the limit for big R, that's going to become a big R. Times, now this is a dot product, so we're going to have the cosine of the angle between the E vector and the ds vector, which we see here is 180 degrees. We'll plug that in a minute. Multiplied by ds, but ds is going in that direction. ds is measured from infinity. What we want to do is we want to convert that into dr, which is measured from the point charge. And that's why this ds becomes minus dr, like that. Okay, so that was the purpose of doing that right there, doing that substitution. All right, let's take this and we can simplify it a little bit. We can factor out some constants. We can factor out q over 4 pi epsilon naught, and we have the integral from infinity to big R of dr over r squared. You might say, well, what happened to the negative signs here? Well, remember the cosine of 180 degrees, that's -1. So that negative and that negative canceled. This negative is still there then. Okay, so we'll do that integral. This is just minus q over 4 pi epsilon naught, and this is going to be -1 over r, and we evaluate that from infinity to big R. And when we do that, we get that the potential is equal to 1 over 4 pi epsilon naught times q over r for a point charge. Big R. So there we have the relationship for the potential, a distance r away from a point charge, and we derived it using this expression, which is the relationship between potential difference and electric field here. Now, you can think of that as just k q over r in general. That's the potential for a point charge in general. Okay, now from this, potential itself is a scalar. Recall that it is a scalar quantity. And because it is a scalar quantity, the sign of this charge matters. The potential can be positive if the charge is positive. It can be negative if the charge is negative. It could also be zero if there's no charge. The potential can be zero. Now, in our case here, we chose to start at infinity. But what if we had not started at infinity? What if we started some initial position and ended up at some final position there? Well, then in that case, V final minus V initial is just K Q over R final minus K Q over R initial, like that. So going between any two positions, then the potential difference is given by this equation here. The potential at infinity, at R of infinity here, is going to cause this second term to be zero then, and we're just left with KQ over R. Now that probably reminds you that the electric field in the force equations, so for Coulomb's law, we had K Q1 Q2 over R squared. And for that one, we had to have two charges. We had to have a Q1 charge, a Q2 charge, that are separated by some distance R, and there's going to be forces along the line between those two. Well, the electric field equation then is K Q over R squared. And for that one, we just have some charge, Q, that has electric field lines going outward. And if you want to know the magnitude of the electric field some distance R away, then it's given by this equation. See, the charge itself generates the electric field. There's no need for a second charge the way there would be up here for a force. But now, for the potential of a point charge, that's just KQ over R. So if we have a point charge here, positive or negative, you know that the electric field lines are going out just like this up here. But if we're some distance R away now, this potential is a property of the field itself. So the potential at this point would be the same as at this point if those distances R were the same in both cases. So for a charge Q, a distance R away, the potential is given by that equation right there. And this is a vector quantity, and this is a vector quantity, but this is a scalar quantity. The potential is a scalar quantity. Okay, because it's a scalar quantity then, if you have multiple potentials, then the total potential is just the sum of all of the individual potentials. So if you have a situation, let's say like this, well, let's take a square here and we'll put charges on each corner here. So we'll have a Q1 charge there, we'll put a Q2 over here, a Q3, and a Q4 there. Now we can say the sides, even though it kind of looks like a rectangle, we'll call it a square. All the sides here are D. Well, what is the potential? Well, you have to choose a point. So let's pick a point here right in the middle of our square. And that means that these are all the same distance away from each of those charges at that point right there. So this R here, R is the square root of D over 2 squared plus D over 2 squared, and that's going to be 2 D squared over 4 square root, so that's going to be D over square root of 2. Okay, so that's what R is. Okay, now what does that mean? The total potential at that point then is going to be the potential due to charge 1 plus the potential due to charge 2 plus the potential due to charge 3 plus the potential due to charge 4. Now I haven't told you whether or not these charges are positive or negative, but what they are is going to play a role here. So this is going to be what? K and then Q1 over R plus Q2 over R plus Q3 over R plus Q4 over R. There. And that's it. So if you have numeric values for your Q1, Q2, Q3, and your D, then you can figure out what R is, you can figure out what the signs of all of these are and add them all together, and then you have the potential at that point due to this charge distribution here. Okay, let's say then that you have another situation. Another situation that looks something like this. Let's say that I have some electrons that are arranged in a circular pattern here. So I'm just drawing kind of a circle and I'm putting electrons on. So let's put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 electrons. And let's pick a point that's in the center of the circle. That means they're all the same distance away, and that distance is, let's say, big R. Okay, what is the potential at the center of that circle of electrons then? Well, the potential is going to be minus 12e, it's negative 12 electrons, over 4 pi epsilon naught big R. There. That's it. So the potential at the center is given by that right there. Okay, now let me ask you a question. What is E? What is the electric field at that same point at the center? Well, if you'll think about it for a minute, the electric field, if all of these are negative charges, the electric field due to this top charge is going to point that direction. The bottom charge, which is exactly opposite of it, is going to point in that direction. Those two are going to cancel. In the same in this direction, and since everything is the same distance away and there's symmetry here, all of those are going to cancel. So what's E going to be? E is going to be 0 at that point. Okay, so you can have a potential that is not 0 for an electric field that is 0. Keep that in mind. All right, let's change this problem up just a little bit then. Let's say that I take all of these 12 electrons and I put them all over here on one side. So I'm going to put them all over here on one side of the circle. There's still the point, that's still the center. But now I've got my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons over here now. And they are still a distance r away. So what is the potential now? What is the potential at this point now? Well, since we still have 12 electrons, and they are all still a distance r away, the potential is still minus 12e over 4 pi epsilon naught big R. It's still the same. Okay? But what about E now? Is E going to be 0 in that case? And the answer is no. E is not 0. You could figure it out if you wanted to. It would be a little more complicated problem because you would have to do it 12 times, one for each of the 12 electrons, because those are 12 point charges that are distributed along that arc there. But it is not going to be 0 in this case. So the electric field then depends upon the distribution of the charge, not just on the total charges, whereas the potential just depends upon how many charges are present then. Well, let's do another problem where we compute the potential. Let's say the potential for a dipole. Let's draw our dipole here. Plus, minus. The distance between the two is d. This is plus q, and we have minus q down here. And let's pick a point out here somewhere. Let's say the point from the center here out here at some angle, we'll call that angle theta, at that point right there, and that's a distance r away to our point. So what is the potential at that point? Well, for this we will assume that R is on the macroscopic scale, whereas D, if we're talking about a molecular dipole, D is on the nanoscopic macroscopic scale. So this is very small. D is very small compared to R. So we'll just say R is much, much bigger than D. That's our assumption here. Okay, well, the potential is going to be pretty easy. The potential is just the sum of all of the individual potentials from I is equal to 1 to 2, because we have two charges here. You'll just sum up the potential. So it's going to be the potential due to the positive charge plus the potential due to the negative charge. Now, that may have a sign associated with it, but the sign is absorbed inside the V here. Okay? So what is that? That's going to be 1 over 4 pi epsilon naught times, well, let's see, it's going to be Q, the positive Q, over the distance R plus. So it's going to be this distance right here. We'll call that R plus. And this distance here is going to be R minus. So plus, and now we're going to put the sign with the Q there over R minus. All right. So if we factor out the Q's, we got Q over 4 pi epsilon naught. And then we've got this right here, 1 over R plus 1 over R minus, which we should be able to find a common denominator for. The common denominator is going to be R plus multiplied by R minus. So what is this? This is going to be R minus minus R plus here. Now you can probably tell that this is going to be very small. The difference between these two is going to be very small. In fact, because one of these is negative and the R plus is almost the same as R minus because of our assumption here, then this is almost going to be 0. So since we have R much, much bigger than D, we can make an approximation here. Now, here are the approximations we're going to make. First of all, we're going to assume that this bottom part of the fraction here, the R plus times R minus, that's just approximately equal to R squared. Now that should be pretty obvious, since this one is a little a little less than R, and this one is a little more than R. Then you multiply those two together, it's almost the same as taking the middle and squaring it. Okay. Now so that one should be obvious. Here's one that's not so obvious though. If I take R minus and I subtract off R plus, then that's approximately equal to D times the cosine of theta. Now that is not so obvious, and let me show you where that comes from. In order to do this, I'm going to sort of take that and expand it down here. So let's expand. Here's our Q plus Q, down here is our minus Q. This whole distance here is D. And we've got, going off in that direction, we've got R. Going off in that direction, we've got R plus, and going off in that direction, we've got R minus. Okay, now if you look at this, you can draw an angle down here so that it makes a 90 with this. And then this angle, which is theta, is about the same angle as that angle right there. So we'll say that's theta as well. Now, to get technical about it, this angle here is not exactly the same, but because of our assumption that R goes off for a long ways, then this is very close approximation that those two angles are the same. And if those two angles are the same, then you can look here at this cosine, and you can get this distance right here. That distance right there, well, what is that? Well, that's R minus R plus. It's the difference in distance between this top and the bottom here. So the cosine of theta then is going to equal R minus R plus over, well, the hypotenuse, which is just D. So solve for R minus R plus, and you get D cosine theta. So once again, that is an approximation, but it is a very good approximation because of our assumption that R is much, much bigger than D. Okay, well, if that's true, then we can take and substitute those in up here, and we can rewrite it down here. V is going to be Q over 4 pi epsilon naught times d cosine theta over r squared, like that. Okay, there we have the relationship then for the potential distance r away from a dipole at some angle theta. And we can modify this a little bit. We'll simplify it because you recall what the electric dipole moment is. P, this will keep popping up over and over again. P is Q times D, and P is a vector, if you recall, but we're just interested in the magnitude at this stage, so it's just Q times D. So here we've got Q times D, we've got a P. We can write this as P cosine theta over 4 pi epsilon naught over r squared, like that. So here we have the expression for the potential a distance r away from a dipole that has an electric dipole moment of P at some angle theta. All right, so we have used our knowledge of the way potentials work here then to derive that relationship. All right, let's move on for a line of charge. Let's say now that we have a line of charge here. Let's say it's positive charge along this line. And let's call the total distance here of the line, we'll say that is L. And we want to know at the end here, at some point P, right there. Now this is a linear charge distribution. This is not a bunch of point charges put together. So we have a lambda that is constant and uniform along this thing. So what does that mean? That means we could divide this up into little charge segments. So let's take a little section of it here. What's in between there is going to have charge dq on it. And that's some distance away here. We'll just say that that's distance r away. So dq is going to be lambda times whatever this distance is here, and we'll just say that that is dx in there. Okay, and that comes about because lambda is charge per length. So this is dq, the charge, and this is dx, the length. All right, well, we'll divide this up into little sections. You've seen us do this sort of thing before. We're going to integrate from this end at 0 to this end at L. And as we do that, the R is going to change. So what do we need? Let's say that that is D. That's the distance that the point is normal to that line. So perpendicular to the line right there. Okay, if we do that, this one's not too bad, really. dV, remember for a point charge, V is 1 over 4 pi epsilon naught Q over R. So dV is going to be 1 over 4 pi epsilon naught dQ over R, like that. And R is a variable here. Now we need to get this in terms of things that we can integrate. You realize that this is a scalar, so we don't have to worry about things canceling or things like that, like we would if they were vector quantities. So the potential, the total potential, is just going to be the sum of all of the individual dVs, and that's equal to 1 over 4 pi epsilon naught times the integral of all of the dq's over r. Okay, let's see if we can figure this out. Well, dq is just lambda dx. R, though, is this distance. Well, look, as r changes, this distance from here to there also changes. Since we called that dx, we should call this distance x. Now, x is a variable because it's going to go from 0 to L. But r itself is really the square root of x squared plus d squared then. And we've already seen that dq is lambda dx. So if I make those substitutions in here, this is 1 over 4 pi epsilon naught, the integral from 0 to L of lambda dx over the square root of x squared plus d squared. Okay, now that's something that can be integrated. I don't expect you to be able to do something like that in your head, nor would I give you something like that on an exam unless I told you what the integral itself is. But when you perform this integration here, here's what you end up with. You end up with lambda, lambda's a constant, it can come out, over 4 pi epsilon naught times the natural log of x plus the square root of x squared plus d squared, and you need to evaluate that from 0 to L. Okay, now when you plug in L here, you're going to get this, and then you're going to plug in for 0, and you're going to get something else. You're going to get, the x's are going to go to 0. So when you plug in 0, you're going to end up with natural log d. Because it's going to be square root of d squared, it's just going to be d. So you're going to end up with natural log of L plus square root of L squared plus d squared for the first part. And then when you plug in for the bottom limit here, you're going to end up with natural log d. Okay, take advantage of the fact that the difference of natural logs is, in other words, if I have natural log of a minus the natural log of b, that's equal to the natural log of a over b, so the ratio of those two. Take that information, plug in your limits, take that information, and you end up with this. V equals lambda over 4 pi epsilon naught natural log of L plus the square root of L squared plus d squared over d. And there you have the potential for a line of charge. So now we have derived the equation for the potential due to a line of charge. Now, there are lots of other examples of this in your textbook. I would encourage you to go look in your textbook to see how they derive potential for various charge distributions. Okay? But we've done enough. And on the exam, I won't give you anything too difficult, but you should expect to be able to have to derive an expression for the potential given an electric field or given a charge distribution.